See, previously we have seen the introduction of HDFS. Okay, when we introduction of the Hadoop. Hadoop was developed by the Apache. Okay, Apache team, basing on the papers published by the Google. Okay, Dove Cutting is the team leader of the team who has developed this Hadoop. And Hadoop is completely written in Java. And Hadoop is nowadays used by Facebook, Yahoo, Google, etc. All these people are using this Hadoop. And when we come to this Hadoop, okay, when we come to the Hadoop, sorry, not components of HDFS, it is actually components of Hadoop. When we come to the Hadoop, Hadoop has mainly two components are there, HDFS and MapReduce. HDFS is used for storing the files. MapReduce is used for processing the files. For analyzing the files, MapReduce. For storing the files, HDFS. Okay, sorry, this heading is wrong. Components of not HDFS. It is components of Hadoop. Hadoop has two main components, HDFS and MapReduce. Already we told HDFS is for storing, MapReduce is for processing the data. When we come to HDFS, one more time I'm repeating, already I have repeated in the previous class. HDFS is a special file system with a cluster of commodity hardware with a stream access pattern. In one line, if anybody asks you about HDFS, our answer it is a special file system with a cluster of commodity hardware with a stream access pattern. Here cluster means a group of commodity hardware means cheap and inexpensive hardware components. A HDFS is a group of cheap and inexpensive components. Okay, it is a group of machines which are inexpensive machines. Some hundreds of thousands of machines will be there in the Hadoop group, but they are very inexpensive machines only we are using in that one. The computers we are using in that cluster is very inexpensive. Commodity hardware means cheap and inexpensive components. Clear? A Hadoop is a special cluster of commodity hardware. Cluster of commodity hardware means a group of cheap and inexpensive components, that is machines. With the stream access pattern, stream access pattern means, okay, the meaning of this stream access pattern is that, okay, write once to the Hadoop, read any number of times. So write once, read any number of times, but don't try to change the file. Okay, the slogan of this stream access pattern is, the main theme of this stream access pattern is write once. That means write the file to the Hadoop once. Read any number of times. You can read the file any number of times, but don't try to modify the data of the file. Write once, read any number of times, but don't try to modify the data. That is the stream access pattern. In one line answer, what is the stream access pattern? The concept is write once, read any number of times, but don't try to modify the data. That is clear. Now, when we come to the first point, Hadoop is a special file system. Why Hadoop is a special file system means, it has mainly 3 points are there. In Hadoop, when we install Hadoop in our system, your hard disk is partitioned into 64 MB blocks instead of 4 KB blocks. In the normal file system, our hard disk is partitioned into 4 KB blocks. Each block size is 4 KB. When we install Hadoop, your hard disk will be partitioned into 64 MB blocks. That is the one specialty. One reason why it is special means, here the block size is 64 MB instead of 4 KB blocks in normal file system. The second point is, in Hadoop block, okay, in case of Hadoop block, there is no chance of internal fragmentation. That means internal fragmentation means, whenever there is a free space in the block after storing the file, if a free space is there in the block, that free space will not be wasted. For example, here in the Hadoop, the block size is 64 MB. If you have a file of 60 MB, you store that file in a single block. After storing that 60 MB block file in that block, 4 MB is remaining space is there. That 4 MB will not be wasted in case of Hadoop. Okay, another file can use that 4 MB. But when we come to normal file system, the block size is 4 KB. For example, if we have a file of 2 KB, the 2 KB file will be stored in the 4 KB block. Remaining 2 KB space is going to be wasted. That 2 KB cannot be used by any other file. That's why in case of normal file system, we have internal fragmentation. When we come to the Hadoop, there is no chance of internal fragmentation. Next, since here the block size is more, okay, the metadata size will be less when we compare with the normal file system. When we compare with the normal file system, here the block sizes are 4 KB. So if we have 100 MB file is there, how many 4 KBs we have to divide that file? Since each block size is 4 KB, we have to divide that file into a lot of 4 KB block files, partitions. Why? Because each block size is only 4 KB. So you have to divide that 100 MB into number of 4 KB blocks, parts. So the metadata will be increased. If we come to Hadoop, if you take same 100 MB, since each block size is 64 MB, how many partitions we have to make our file? Our file will be divided into just two parts. First part will take 164 MB. Second part will take another 64 MB block. So only two blocks are there. So we have to store only two blocks information. When we come to Hadoop for 100 MB file, just two blocks information we have to save. When we come to the normal file system, lot of 4 KB blocks will be used. So we have to store all those data. So that's why, because of these 3 points, we said HDFS is a special file system. Why? Because block size is 64 MB, which is very much greater than 4 KB block. There is no chance of internal wastage of memory. Metadata is also less when we compare with normal file system. That's why HDFS is a special file system with a cluster of commodity hardware, that means group of inexpensive machines with the stream access pattern, with the logic that write once, read any number of times, but don't try to modify the data logic. That is HDFS. Okay. When we come to this one, already we told HDFS main purpose is for storing the files. When we come to HDFS, the role of HDFS is for storing the files, whereas the role of MapReduce is for processing the files. So we will see only the HDFS. When we come to the HDFS, there are 5 services are there: name node, secondary name node, job tracker, data node, task tracker. Okay, there are 5 nodes are available in the HDFS. Totally 5 nodes are there. These are called as HDFS services, HDFS nodes, or HDFS daemons. We can call these 5 as HDFS services or HDFS nodes or HDFS daemons. Daemons means background running process jobs. What is a daemon? Daemon means background running process or program is called a daemon. Background running program is called a daemon. These are also running background, directly not visible to the programmer or client. That's why these are called daemons. These can be called as HDFS services or nodes or daemons, whatever the name used by any person. Some people will call them as nodes, some people will call them as services, some others will call them as daemons. Whatever, HDFS has mainly 5 daemons are there: name node, secondary name node, job tracker, data node, and task tracker. When we come to the first 3, the first 3 are called master daemons or master nodes or master services. Whatever the name you are using, these are called master services or master nodes or master daemons. The first 3 are called the master machines. The second 2 are called the slaves. Okay, automatically opposite of that one. These 2 are called slave daemons or slave nodes or slave services. Whatever you call them as master nodes, slave nodes, master daemons, slave daemons, master services, slave services. Is it clear? First point is these 3 belongs to master, these 3 belongs to the slave. And when we come to this, okay, any node in the master can communicate with another node in the master directly. Any node in the master can directly communicate with any node in the master, another node in the master. Name node can directly contact secondary name node or job tracker. Job tracker can directly contact secondary name node or master. They can internally call anyone. Any node can communicate with any other node. Similarly, when we come to the slave also, in the slave also, data node can happily communicate with the task tracker. Task tracker can happily communicate with data nodes. Okay, when we come to the slave part, the nodes in the slave part can communicate with one another directly. The nodes in the master part can communicate with one another directly. But when we come to the master nodes and slave nodes, okay, from the master node, only name node can communicate with data node in slave part. From the master node, only name node can communicate with data node in the slave part. Okay, we can call this master node as master node is the master for the data node. Data node is called as the slave of name node. Okay, the name node can only is the act as master for the data node, or master or the superior for this data node. Data node will act as slave for the name node. Okay. In the see, inside the master part, anyone can communicate with another. But when we come to the master part, only name node in master part can communicate with data node. Name node cannot contact task tracker. Okay. Name node cannot contact task tracker. Only name node can communicate with data node. Similarly, job tracker can only contact the task tracker. From the master part, who can communicate with the task tracker means only job tracker can communicate with the task tracker. Here also we can call this job tracker as the master for task tracker. Task tracker is called as slave for the job tracker. Job tracker is the superior, task tracker is the subordinate. Name node is the superior, data node is the subordinate. Clear? Inside the master part, anyone can communicate with one another. Inside the slave part, anyone can communicate with one another. But when we come to master part and slave part, in master part, only name node can communicate with data part in slave part, data node in slave part. And when we come to master part, only job tracker in master part can communicate with task tracker in slave part. Name node cannot directly contact task tracker. It can't go deal with task tracker. Job tracker cannot talk with data node. Okay. But data node and task tracker can communicate with one another. Name node and job tracker can communicate with one another. Is it clear, guys? These points. Name node, secondary name node, job. These three belongs to master part. These two belongs to the slave part. These communication will be like this. Job tracker is the superior for the task tracker. Name node is the superior for the data node. Is it clear, guys? And when we come to this one, okay. Now, when we go to for operation of this HDFS, see, whenever a client wants to store some file, whenever a client wants to store his files in the Hadoop, already we know Hadoop is a cluster of commodity hardware. Hundreds of systems will be connected one another. Okay, it is a cluster. Among all those systems in the cluster, one system will act as the name node. Remaining all the systems will be the data nodes. Okay, one system will act as the name node. Remaining systems will act as the data nodes. The client will communicate with the name node. Whenever the client wants to store some data, some file in the Hadoop, in the HDFS, whenever he wants to store some files in the HDFS, first the client will communicate with name node. He will go to approach name node and he will ask the name node, I want to store some files in your database. Sorry, in your file system, I want to store some files. My file, I have a file. I want to store that file in your file system. Clear? For example, client has a file. This is the file name .txt, f.txt. He has a file with the name f.txt. He has a file. He wants to store this f.txt in the HDFS. So he communicated to the name node. I want to store my file f.txt in your location. Okay. See, when we come to the Hadoop, already we told what is the size of the each block. Okay. Internally, when we are storing the files, the data, the file block size is only 64 MB. So first, what the name node will do is depend. For example, if the file size is 200 MB, if the file size is 200 MB, it will partition this file into how many for 64 MB files we want? 64 into 4. 4 6 are 24. 64 into 3. 3 6 are 180. 3 4 are 192. So nearly 4 partitions will be formed. File a.txt. The first partition is a.txt. Second one, for example, the second part is named as b.txt. Third one, c.txt. Fourth one, d.txt. Clear? 64 MB, 64 MB, 64 MB. I think remaining space will be here. 3 6 are 180, 3 4 are 192. Remaining 8 MB will be here. Clear? Your f.txt 200 MB. The client want to store that file, so he communicated with the name node. Okay, basing on the size of this 200 MB, first now name node will divide that one into partitions. Why? Because his block size is only 64 MB. So 4 parts will be divided. That given file is divided into 4 parts. Okay. Next, he will maintain the data. Okay, he will maintain the data in the metadata. He will maintain immediately the name node will open the metadata, and he will store the information A, B, C, D. He will enter the names A, B, C, D into that metadata. Next, what the name node will do is he knows out of all the data nodes available, which data nodes are currently available free. He will know the status of each data node. So he will pass that information. He will pass the information about the data nodes to the client. Okay, he will reply to the client. Okay, you can happily store your files in the following data nodes. For example, the data nodes names are 1, 2, 3, 4. For example, another data node is there 5, like this. Okay, he said 5. How many 5? These are available? 4 are available. So he will pass. You can store your file in data node 2, 4, 1, 5. Like that, he will give the numbers. He will reply. The name node will reply to the client. You can store your file, your partitions of the files in the following machines, data nodes. So immediately client will communicate with the data nodes. Okay. For example, he want to store file a.txt. What is the node data node number? For example, the data node number for the first one is 1, 1, 2, 4, 5. So first he will communicate with data node and he will store a.txt in this one. In the data node 1, client will store the a.txt. Similarly, b.txt will be stored in the data node 4. b.txt will be stored. Similarly, c.txt in the data node 2. Data node 5 will be stored in D will be stored in data node 5. See, A.txt in node 1, B.txt in node 4, C.txt in node 2, D.txt in 5. Your original file is divided into 4 partitions. 4 partitions are stored in 4 different blocks. Clear? Immediately, the name node will update the metadata with locations where we stored the node first A.txt in name node 1, B, name node 4, C, name node 2, D, data node 5. A is available in data node 1, B is available in data node 4, C is available in data node 2, D is available in data node 5. He will update. Clear? In this way, whenever the client came to the name node, I want to store a file, simply he will get the data about the data node. He has the full data about which data nodes are currently free, available. That is basing on that information, he will decide how many data nodes are required. That numbers will pass to the client. So the client will directly communicate with the data nodes and he will store his data in that one. Clear? He will communicate with that one. He will store his files. Okay, basing on the name node, data node numbers given by the name node, client will store his partitions in the blocks of the data nodes. This is first how it is storing. Here one question will rise. Say, if you store the first part in data node 1, second part is in data node 4, third part is in data node 2, fourth part is in data node 5. The question will get is, due to some problem, see, we are using which hardware here? Commodity hardware. That means inexpensive and cheap hardware we are using. All the data nodes are not reliable components. They are very cheap components. He is maintaining with them in the cheap components only. So there is a more chance of failure of the devices. Why? Because regularly he is using the cheap components only. As he is using the cheap component, there is a more chance of failure. So for example, if data node A1 failed, if this node is failed, what will happen? Automatically A.txt will be lost. Then how to recover that one? Then what we have to do? Mana data node, mana use chesende commodity hardware. All the data nodes are inexpensive components, cheap components. So there is a more chance that the machines will fail to work. If any data node is failed, okay, what will happen? The data in the data node will be lost. The partition will be lost. So how to recover that one? Data node 1 fail అయితే A.txt మిస్ అయిపోతుంది. దాన్ని ఎలా రెక్టిఫై చేసుకుంటుంది? How it will get? For that purpose, what the HDFS will store is, whenever a partition came into the HDFS, whenever a partition has came into the HDFS, like in GFS, it will also replicate the data 3 times. Okay, 3 copies of the data will be stored in 3 different data nodes. Clear? First, a.txt, originally the client sent a.txt to data node 1. That means 1 copy of a.txt was saved. Immediately, data node 1 will send the same copy of a.txt to another nearby data node. Another nearby data node which is free, which has space. It will send a copy of a.txt to another data node also. A.txt. See, client has sent the a.txt to data node 1. One copy of the same a.txt was sent by data node 1 to data node 2. Data node 2 will send one more copy to, for example, data node 4, a.txt. Originally, the client sent that copy to only data node 1, but internally, same copy is maintained in data node 2 as well as data node 4. That information will also updated in the metadata. Now, where A is stored in 3 different data nodes. 1. Okay, name node will update 1 to 4. 1 to 4. Similarly, for 2 BCD also. For example, BCD are in 4, 5, 3, 2, 3, 6, 5, 7, 9. For example, we are taking. That means for every copy, minimum 3 copies of the same, each partition is stored. So that the answer is there. Internally, whenever data node 1 is failed, immediately the a.txt is not lost. It is in data node 2 or 4. So that name node will go for 2 or 4 to get the data. Whenever data node 2 is failed, okay, C will not be missed. C.txt will not be missed even though data node 2 is failed. Why? Because it is still available in 2 more, 3 and 6. Data node 2 is available in 3, 6. Okay, D, 5, 7, 9, like that. So the question is, after client stored the data for the data partitions in the data nodes, how the data is secure? If there is any failure in the hardware, how he will maintain the data means internally HDFS will replicate each data file 2 copies. Okay, whenever a file has came to the data node, it will maintain 3 duplicate copies. Instead of storing only 1 copy, it will store 3 copies in 3 different data nodes. So that when any data node is failed, the data will not be lost. Okay, it will maintain a minimum of 3. By default, it will maintain 3 copies. If the client wants, he can increase the number of copies also. Like GFS, similar to GFS in HDFS also, minimum 3 copies will be maintained. Okay, and if the client wants, he can increase those copies also. So that one question has solved, one problem is solved. If the data node is missed happily, other from the other data node they will get. Clear? Now here internally what is happening is name node is regularly communicates with the data nodes. Okay, name node will regularly for every time period of time, name node will get information from the data nodes. Okay, for every period of time, data node will send 2 informations to the name node. One information is heartbeat. It's the heartbeat. For every period of time, for example, the period of time is 2 minutes. For every 2 minutes, the data nodes will send 2 informations to the name node. One information is it's the heartbeat. The other information is block report. Okay, one information is its heartbeat. The other information is block report. What is the heartbeat indicates means the heartbeat of data node indicates that it is alive. I am alive, I am active, I am working. To indicate that the data node is working, it is active and live. Every data node will send its heartbeat to the name node for every period of time. For every period of time, depending on the set by the administrator, for that period of time, data node will send heartbeat to the name node. For example, if the time set is 2 minutes, for every 2 minutes, it will send its heartbeat to the name node, so that the name node will understand data node 1 is live, data node 2 is live, 3 is live, 4 is live. If no, next, similarly, along with the heartbeat, it will send block report also to the name node. What is this block report contains? Already we told when we come to the data node machine, the hard disk is divided into 64 MB blocks. Okay, the block report indicates in the data node how many blocks are free now, how many blocks are free now, how many blocks are filled by which files. That information will be given by to the name node. Okay, every data node will send a block report to the name node for a period of time. In that block report, it will indicate that at present in my system, okay, 100 blocks are free. Remaining 100 blocks are filled with these files. First block is filled with this file. Second block is filled with this file. Third block is filled with this file. Like that, it will give the complete report about the status of their blocks. Data node 1 will send a block name node. Data 2 node 2 will send a block name node. Data 3 node 3 will send a block name node. Data 4 node 4 will send a block name node. Data 5 node 5 will send a block name node. Data 6 node 6 will send a block name node. Data 7 node 7 will send a block name node. If any data node doesn't send block report, means name node understands that that particular data node is not working. It is not live. Okay, for example, for every 2 minutes, data nodes have to send the block report and heartbeats to name node. After 2 minutes also, if heartbeat doesn't came to the name node from data node to heartbeat doesn't came to name node, even after 2 minutes, then name node confirms that name node 2 is data node 2 is not working. Clear? For every period of time, data nodes will send heartbeats as well as the block reports to the name node. So that for every period of time, name node has complete information. In each data node, these blocks are available. These blocks are filled with this data. It has complete metadata is available at the name node. So whenever a client came to name node, I want to store a file of this size. Immediately name node, based on the information given by the data nodes, name node will identify, okay, these data nodes are free to store the partitions. So it will decide, it will identify and it will send the data node numbers to the client. You can store your file in the following data nodes. How it is sending these numbers means you can store your file in 1425. How it is sending? Why? Because for every period of time, data nodes will give you a response to the name node. Okay, basing on the heartbeat and block and for block report given by the data nodes to the name node will decide which blocks are available for client, which data nodes are available for the client. That the client will communicate with those data nodes and it will store its data in those corresponding data nodes. Clear, guys? This is the first thing, how to store the data. Whenever the client wants, client will approach name node. Name node will, basing on the information available at name node will send data node numbers to the client. You can store your file in the following data nodes. Then client will approach the data nodes to store his partitions. Okay, basing on the size, he will divide that file into partitions. That partitions will be stored in the corresponding data nodes. Okay, all this information will be updated in the metadata available at the name node. Okay, all the information is updated at the metadata available at the name node. Whenever any data node is failed, how name node knows means for every period of time, name node will get heartbeat and block report from the all data nodes. So that basing on the reply came from the heart in the form of heartbeats and block report, name node will know every period of time, name node will know the status of every data node, whether all data nodes are working properly or not, how much space is available in each data node, like that, all that information. And one more question is, since we are using the commodity hardware, whenever the data node is failed, whenever a data node is failed, why? Because we are using the inexpensive components only. What will happen means, since even though when there is a more chance of failure of the data nodes, why? Because we are using the commodity hardware in that cluster. So there are more chances for failure of hardware. That's why the HDFS will maintain 3 copies of each file. Whenever a file has came to the HDFS data nodes, internally the data nodes will store the same file in 3 copies in 3 different data nodes. Okay, it will maintain a minimum of 3 copies of the file in 3 different data nodes, so that Any data node is missed, no problem at all. The same file can be get from another two data nodes. Clear? That is the thing. And one more question will be there. Where is all this metadata? All the metadata is stored at the name node. The question is, if data nodes are failed, no problem at all. The same data is available in other name nodes, so we will get the data from other data nodes. What will happen if name node is failed? What will happen if name node is? The question will come to the name node also. See, name node is a crucial one, very most important one in the HDFS. When the name node is failed, your Hadoop will not work. Okay, your entire Hadoop will stop working. Whenever the name node is failed, name node will play a major role, crucial role in the total HDFS. So if the data nodes are failed, no problem at all. Happily, we can get the same data from other data nodes. Why? Because 3 copies we are storing in 3 different data nodes. But when we come to the name nodes, for every HDFS Hadoop cluster, only one name node is there. There is no other name nodes are there. So whenever the name node is failed, you will lose all the metadata. You will lose all the metadata, and the operation of the HDFS will stop totally. If the name node is failed, the entire Hadoop working will be stopped. So name node is a crucial one, important one. That's why when we come to the HDFS, all the data nodes are commodity hardware, but name node is not a commodity hardware. Okay, it is a very good, reliable machine. For the name node, we don't use the commodity hardware, which has the more chances of failure. For name node, we will use a high reliable machine, high reliable hardware, which has single point of failure. Name node is a single point of failure. That means it has very less chances to failure. Name node has very less chances to failure. Okay, it is a high reliable machine. In the place of for name node, we will use very high reliable machine. Why? Because if no name node fails, there is no alternative for name node. Your entire Hadoop operation will be stopped. That's why name node machine is very important machine. But data node machines have no problem at all. Okay, they are only cheap machines only. We are using cheap machines for data nodes. Why? Because for every file there is 3 copies are there. Even though one data node is not failed, no problem at all. Happily we will take the copy from another one. But name node is a crucial one. Okay, that's why for name node we use very high reliable components. The hardware used for the name node is a very high reliable hardware. Okay, that means it has very less chances of failure. It is called as the name node is called as a single point of failure. Single point of failure. Okay, that means it has very less chances for failure. Clear? Data nodes are inexpensive and commodity hardware, but name node is a high reliable hardware. It is a expensive and high reliable hardware. That is the thing. For name node machine, we use the high reliable hardware instead of using the inexpensive and cheap hardware. Why? Because name node is a crucial person. It should not fail frequently. Whereas when we come to data nodes, it can happily fail frequently. No, even though data node failed frequently, we have no problem at all. The operation will not be stopped. Clear? This is what is happening first part. Okay, how to store a file in the HDFS. Okay, client will approach name node. Name node will give the basing on the information given by the data node. Name node will give the data node numbers to the client. Client will approach the data nodes and he will store his partitions in the corresponding name nodes. Sorry, in the corresponding data nodes. All this information is updated in the metadata, which is maintained by the name node. For preventing the loss of data, when the data nodes failed, for each file copy, there is it will maintain 3 copies. For each file, it will internally maintain 3 copies in 3 different data nodes. So that even though any particular data node is failed, no problem at all. The file is still available in 2 more copies. Clear? Like that, it will maintain the reliability. But when we come to the case of name node is a single point of failure. That means it is a high reliable machine, high reliable hardware machine. So that it has very less chances of failure. If the name node is failed, there is no alternative for name node. Until you place a new name node in that place, the Hadoop will not work. If name node fails, until you replace name node, your entire Hadoop operation will be stopped. But when data nodes fail, no problem at all. Hadoop will still continue to work even though some particular data nodes are failed to work. Clear, this is the first thing. Here we are discussing name nodes and data nodes. Here important points is data node is the machine which is actually storing the file parts. Where we are storing the file means the files are actually stored in the data nodes. Name node is a machine, but actually in the name node only name node will maintain the metadata. Actual data will not be stored in the name node. Actual files will not be stored in the name node. The name node only stores the metadata of the file, whereas data nodes will store the actual files. Your actual files will be stored in the data nodes. Like in GFS, master server will not store the file chunks in the GFS. It will only maintain metadata. Chunk servers will actually store the file chunks. Similarly, in the HDFS also, okay,